On the 4th of May 2026, at precisely 2032 Coordinated Universal Time, something struck Earth's magnetic field, and the scientists watching the instruments had not predicted it was coming. Not at that strength, not with that orientation, not from whatever it was. The KP index, the global measure of geomagnetic disturbance that forecasters had expected to sit quietly between 3 and 4, surged to 6. The G2 storm threshold was crossed, and when space weather analysts at NOAA's Space Weather Prediction Center sat down to explain it, the answer they published, the official answer from the most advanced solar monitoring network in human history, was this: scientists aren't sure. But that is not even the real story. The real story is not one surprise storm on one quiet night in May. The real story is what that surprise reveals about the limits of what we can see, what we cannot predict, and what is silently building above us right now as you watch this. Because the storm that blindsided forecasters on May 4th was not, by itself, extreme. A G2 event is what the professionals call moderate. It disrupted high-frequency radio communications over the Pacific, expanded the auroral oval to Alaska, northern Canada, Iceland, and the high latitudes of Scandinavia, and induced geomagnetic currents in the ground beneath cities and transmission lines. G2 is alarming, but G2 is not catastrophic. What makes this story genuinely alarming is the sequence of facts that surrounds it. The fact that the CME responsible for it, the coronal mass ejection, the multi-billion-ton plasma bullet that traveled 150 million kilometers from the surface of the Sun to collide with our magnetosphere, arrived without being seen. The fact that the magnetic field it carried was oriented in precisely the most dangerous direction possible, pointing southward, opening Earth's magnetic shield like a door pushed from the wrong side. The fact that this orientation held for 15 straight hours. And the fact that we are right now in the peak phase of solar cycle 25, a cycle that was predicted to be moderate, that was predicted to behave, and that has instead broken nearly every forecast it was given. The sun is not dormant, the sun is awake, and it is not finished. Let us start with exactly what happened, because the data deserves to be heard plainly before it is interpreted. For several days prior to May 4th, solar activity had been relatively subdued. Active region AR4424 fired an M1.8 flare, a moderate eruption, at 01:13 UTC on May 4th, which triggered an R1 minor radio blackout that briefly disrupted high-frequency communications across the Pacific and Eastern Asia. That flare came from beyond the western limb of the Sun, meaning the blast was already rotating away from Earth's direction. There were no confirmed Earth-directed coronal mass ejections visible in coronagraph imagery. Solar wind speeds were at moderate low levels. Everything pointed toward a quiet few days. Forecasters at the Space Weather Prediction Center issued an outlook calling for a slight chance of G1 minor storming, one step above nothing. Then 2032 UTC arrived, and the KP index went to 6. What hit Earth was what NOAA subsequently described as a slow-moving, favorably oriented transient feature, a weak coronal mass ejection that had been hurled into space approximately 4 to 6 days earlier, probably around April 30th, probably from an eruption that had not been clearly identified as Earth-directed at the time. It had traveled slowly across interplanetary space, slow enough that it took nearly a week to cross the 150 million kilometers between the Sun and Earth instead of the more typical 2 to 3 days for faster CMEs, and it arrived carrying a southward-directed magnetic field. That word, southward, is the key to understanding everything that happened next, and everything that could still happen. Here is what it means in physical terms. Earth's magnetosphere, the invisible magnetic bubble that surrounds this planet and has protected life here for billions of years, points northward. Its field lines arc from South Pole to North Pole. When the magnetic field embedded in the solar wind also points northward, the two fields partially cancel each other out, they push against one another, and Earth's shield holds. But when the solar wind carries a southward magnetic field, what scientists call a negative Bees component, the fields do not push against each other, they connect, they merge. They undergo a process called magnetic reconnection, and when that happens, the door opens. Solar wind energy that would normally be deflected streams directly into Earth's magnetosphere, and the result is a geomagnetic storm. What the data shows for the May 4th event is that the Bees component of the interplanetary magnetic field pointed southward and stayed there from approximately 15 UTC on May 4th through 06 UTC on May 5th. 15 hours with Earth's magnetic shield held open, with the total interplanetary magnetic field reaching strong levels while the BZ held its southward orientation. The G2 storm was brief in its peak intensity, 1 3-hour period at KP6, but the exposure was prolonged, and forecasters had not seen it coming. Here is where this story becomes genuinely alarming. It is not that one storm was missed. It is that the mechanism by which it was missed is not an anomaly. It is a structural feature of the way space weather works, a fundamental limitation that does not go away with more satellites or better computers. slow coronal mass ejections are genuinely difficult to identify and track. Unlike the fast, energetic eruptions associated with major X-class solar flares, the kind that produce radio blackouts the moment they occur and that show up unmistakably in coronagraph cameras within minutes, a slow, weak CME can leave the sun without a clear associated flare, without a clear origin point, without a clear trajectory, and without triggering the monitoring thresholds that would cause forecasters to issue a watch. The CME responsible for the May 4th storm is believed to have been associated with an eruption that left the sun on approximately April 30th. 6 days traveled across space, arriving with a punch that exceeded anything the models had suggested. And this is the point the data actually makes. It is not the monsters that hide in plain sight. The monsters are sometimes the quiet ones, the ones that drift slowly, the ones that arrive without announcements. Because here is the physics of why southward BZs matters so disproportionately. 85% of all magnetic clouds in the solar wind, according to research published by Lee, Luhmann, and Lynch analyzing 303 magnetic cloud events spanning 1995 to 2017, carry southward BZ up to 50 nanoteslas. The sheath regions preceding these magnetic clouds can themselves carry southward fields up to 40 nanoteslas. The strength of the geomagnetic response is not primarily determined by the raw energy of the CME. It is determined by the orientation of the magnetic field inside it. A weak CME pointing south can hit harder than a fast CME pointing north. That is documented physics. That is what makes prediction so genuinely difficult, and that is what makes the question of what comes next so impossible to answer with confidence. Think about where you are right now. Think about the city you are sitting in. If you're in Northern Europe, in Stockholm, in Oslo, in Helsinki, you experienced enhanced aurora visibility on the night of May 4th, the charged particles raining down your field lines, making the sky glow green and red at latitudes where such displays are common but never entirely routine. If you are in the northern United States, in the upper plains of Canada, in Scotland or Iceland, the same particles made the same sky perform for you. But there are other cities where no light show appeared, where residents went about their evenings without any awareness that something had changed. Cities in New Jersey, where in March 1989 high-voltage transformers melted under the stress of geomagnetically induced currents during a storm far stronger than this one. Cities in Quebec, where those same 1989 currents cascaded through transmission lines within 90 seconds, pulling the entire Hydro-Quebec power grid offline and leaving 6 million people in darkness, in the cold, without warning, without power, for 9 hours, some of them for days. Think about those 6 million people. They woke up on March 13, 1989, and they did not know that something on the surface of the sun 12 days earlier was going to determine their morning. They did not know that solar physics would reach into their kitchen, into their hospital, into their furnace, and take something away. The geomagnetic storm that produced that blackout carried solar wind speeds estimated at 980 kilometers per second and southward interplanetary magnetic field values between 40 and 60 nanoteslas. The X4.5 flare on March 10th had cleared the path in space, reducing the density of the interplanetary medium so that the second CME from the M7.3 on March 12th could travel faster and hit harder. 2 CMEs, one clearing the road for the other. The lights in Quebec went out approximately 90 seconds after arrival, and that 1989 storm, the biggest geomagnetic storm of the space age, in the words of Dr. David Boatler, head of the Space Weather Group at Natural Resources Canada, and lead author of a comprehensive analysis of the event, was itself approximately half the intensity of the Carrington event of September 1859, half the intensity of Carrington. Let that settle. In 1859, an astronomer named Richard Carrington was sketching sunspots at his observatory outside London when he observed 2 brilliant white flashes of light erupting from a cluster of sunspots. He had never seen anything like it and would never see anything like it again. Within hours, the shockwave from that eruption struck Earth's magnetic field with a force that has not been equaled in recorded history. The Aurora Borealis blazed across the Caribbean. It blazed over Cuba. It blazed so brightly over the Rocky Mountains that gold miners woke up and began making breakfast because they thought it was dawn. Telegraph operators across Europe and North America found that their equipment had come alive, sparking, shocking them, setting telegraph paper on fire, transmitting messages entirely without any battery connected. The geomagnetic storm that Carrington witnessed produced a DEST index, a measurement of the disruption to Earth's magnetic field, estimated at between -800 and -1750 nanoteslas. The 1989 Quebec storm produced a DEST of -640 nanoteslas. The May 4th, 2026 storm produced conditions consistent with moderate KP6 activity, a fraction of either. The evidence for the Carrington event is not speculation. It is preserved in ice cores, in historical records, in the telegraph dispatches of that September night, in the geological record. This has already happened once. The evidence is still there. And a report by the National Academy of Sciences has concluded that a geomagnetic superstorm of Carrington magnitude occurring today would cause continent-wide loss of electricity, substantial damage to power grid infrastructure that would persist not for hours but for months, and economic costs to the United States alone in excess of $1 trillion. Other analyses put that figure closer to $2 trillion. And what the data actually shows is that solar cycle 25 has given us precisely the kind of active solar environment in which extreme events become not theoretical but probable. The sun was predicted to behave modestly. It was not consulted on the matter. When an international panel of solar physicists convened by NOAA, NASA, and the International Space Environment Services published its solar cycle 25 prediction in 2019, they forecast a maximum smooth sunspot number of approximately 115, with the peak occurring around July 2025. They expected cycle 25 to be a quiet cycle, comparable to the anemic cycle 24 that preceded it. By 2023, the sun had already exceeded those predictions. By 2024, it had shattered them. The updated NOAA forecast revised the expected peak to between 137 and 173 sunspots, and of a massive revision, and placed the peak between January and October 2024. The smooth sunspot number reached 156.7 in August 2024. And then the sun did something that cycles sometimes do and that models rarely anticipate. It showed signs of a double peak. Solar cycle 24 had peaked twice, in 2012 and again in 2014. Solar cycle 25 may be doing the same thing. The activity that was supposed to be declining is not clearly declining. Active sunspot regions keep emerging. Active region AR4366 alone, which emerged on January 30th, 2026, produced 21 C-class flares, 38 M-class flares, and 6 X-class flares before it rotated off the disk. One region, one patch of the sun's surface producing 6 X-class explosions. SpaceWeather.com described AR4366 as shaping up to be the most active sunspot of solar cycle 25. And now, as of May 6, 2026, a large new coronal hole has rotated to near the center of the solar disk. Coronal holes are regions where the sun's magnetic field opens outward into space like a wound that will not close, allowing solar wind to stream out at speeds far higher than normal. That hole will deliver its elevated solar wind stream to Earth in the next 2 to 3 days. More G1 conditions are possible. More enhanced geomagnetic activity is coming. The system is not dormant. The system is awake. There are approximately 8,500 active satellites in Earth orbit right now. Every one of them is operating in an environment that directly responds to what the sun does. When solar activity expands the upper atmosphere, when the thermosphere heats and swells upward under the bombardment of solar ultraviolet and particle radiation, satellites in low Earth orbit experience increased drag. They slow down. Their orbits decay faster. In February 2022, SpaceX launched 40 Starlink satellites into low Earth orbit and lost them within 24 hours because a moderate geomagnetic storm expanded the atmosphere enough to increase drag to levels the satellites could not overcome. 40 satellites, gone because of space weather. The Thermosphere Climate Index, which measures the heat output of Earth's upper atmosphere, stood at 17.03 times 10 to the 10th watts on May 5, 2026. The historical maximum, recorded in October 1957 near the peak of what is considered one of the strongest solar cycles of the modern era, was 49.4 times 10 to the 10th watts. 2. We are not at maximum historical thermal loading, but we are well above quiet conditions, and the coronal hole high-speed stream that is arriving now will push that figure higher. The solar radio flux at 10.7 centimeters, the standard measure of solar output used by satellite operators and atmospheric drag models, stood at 138 solar flux units on May 4th. That is elevated. That is active. That is the background against which this mystery CME arrived, and GPS. The question of what a geomagnetic storm does to GPS is not technical trivia. It is a question of how hospitals communicate, how aircraft navigate over polar routes, how financial transactions are time-stamped, how emergency services dispatch responders, how container ships find port in poor weather, how power companies synchronize their grids. During a G2 storm, GPS accuracy degrades. During a G3 or G4 storm, GPS accuracy can be lost entirely over wide regions, particularly at high latitudes. The GPS system was not designed for the space weather environment of a strong solar maximum. It was designed in an era when cycle 24, that quiet, weak cycle, seemed to represent the new normal. Solar cycle 25 has corrected that assumption. The question is not whether the system is vulnerable. The question is when the storm comes that is large enough to demonstrate exactly how vulnerable. Here is the thing about the May 4th storm that should not be lost in the technical language. The B's component held southward for 15 hours. That is not a brief dip. That is not a momentary fluctuation. That is a sustained opening of Earth's magnetic shield lasting more than half a day. During those 15 hours, every power grid operating at high latitudes, every satellite in low Earth orbit, every high-frequency radio operator trying to communicate across the Pacific and over Eastern Asia was operating in a degraded environment. The R1 radio blackout from the M1.8 flare had already disrupted communications. Then the CME arrived and the geomagnetic environment worsened further, and forecasters had issued a slight chance of G1, not G2, not 15 hours of southward BZs, a slight chance of G1. This is not a criticism of the forecasters. The science of space weather prediction is genuinely difficult in ways that have no easy technical solution. Coronagraph instruments aboard SOHO, the Solar and Heliospheric Observatory, and the stereo spacecraft can see CMEs leaving the Sun, but they cannot reliably determine the internal magnetic orientation of the CME, the direction of the BZ field, that will ultimately determine whether a storm is G0 or G5. That determination can only be made when the CME arrives at the L1 Lagrange point, the point in space approximately 1.5 million kilometers from Earth, where NOAA's Descovier satellite and the newer SWFO L1 observatory monitor the solar wind in real time. At that point, scientists have between 15 minutes and an hour of warning before the CME hits Earth's magnetosphere. 15 minutes. That is the warning time for the most consequential piece of information, the magnetic orientation, in the entire space weather prediction chain. The monitoring is in place and detection is possible, but prediction is not. And that sentence, heard clearly, carries its own warning. We have to talk about what stacks on top of this. Because what happened on May 4th did not occur in isolation. It occurred during the active phase of a solar maximum that has exceeded every model that was built to contain it. It occurred while a large coronal hole sits centered on the solar disk, preparing to deliver another high-speed stream. It occurred while active regions AR44424 and the emerging regions visible on the northeastern limb continue to show magnetic complexity. And it occurred during what researchers at onoff.gr and Climate Cosmos, synthesizing NOAA and NASA data, have described as a cycle that is still producing strong X-class flares in 2026. Even as the smoothed sunspot number begins, tentatively, to decline from its 2024 peak. The declining phase of a solar cycle is not a safe zone. Some of the most significant geomagnetic storms in history occurred years after the sunspot maximum. The Halloween storms of October and November 2003, which produced G5 extreme geomagnetic conditions and caused power outages in Sweden, damaged over a dozen satellites, forced high-altitude aircraft to divert from polar routes, and produced aurora visible as far south as Texas and Florida. Those storms occurred in the declining phase of solar cycle 23. The monster does not go away because the number of sunspots starts dropping. It sometimes gets more unpredictable. Think about Reykjavik, Iceland. Think about the roughly 130,000 people who live in and around that city, in a nation that sits directly under the auroral oval, that operates geothermal power infrastructure, that relies on submarine communications cables, that depends on GPS navigation for its fishing fleet, a fishing industry that generates a significant fraction of the national economy. On the night of May 4th, the skies over Reykjavik lit up. Auroras pushed south, bright and active, the kind of display that makes residents look up from their phones. Beautiful, undeniably beautiful. But the same particles making that beauty were the particles inducing geomagnetically induced currents in the ground, in the cables, in the infrastructure. GICs, geomagnetically induced currents, are the slow, silent side effect of a geomagnetic storm. They flow through any long conductor that runs along the ground. Pipelines, power transmission lines, telephone cables, railway lines. They corrode metal over time. During extreme events, they saturate power transformers, causing them to overheat, sometimes within seconds. High-voltage transformers are not stockpiled items. A large power transformer takes between 12 and 18 months to manufacture and weighs several hundred tons. If a sufficient number of them fail simultaneously, as the National Academy of Sciences analysis concluded could happen in a Carrington-level event, there is no rapid recovery pathway. 6 million people in Quebec in 1989 waited 9 hours. The National Academy of Sciences projected that a Carrington-equivalent event could leave large portions of North America without electricity for months. Now think about the specific sequence of events that produced the May 4th storm. A CME left the Sun around April 30th. It was slow. It was weak. It was not clearly identified as Earth-directed in the coronagraph imagery. It traveled for approximately 4 to 6 days across interplanetary space. It arrived carrying a southward magnetic field. It combined with the elevated solar wind conditions created by a coronal whole high-speed stream. And the result was a G2 storm that exceeded the forecast by a full-scale level. The Earth Sky Science reporting team, monitoring the instruments in real time, described the surprise plainly. Forecasters had noted a slight chance of G1 storming, and the disturbance was much stronger than expected. The reason? Scientists aren't sure. Those 4 words, scientists aren't sure, are not a failure of the scientists. They are a statement about the physics. The internal magnetic structure of a CME is set deep inside the Sun, in the dynamics of the erupting magnetic field in a region that no instrument has ever directly sampled. It is carried across space, invisible in its most dangerous characteristic until it reaches L1, 15 minutes of warning. For a planet with 8 billion people and a technological civilization that depends on the electromagnetic stability of near-Earth space, the way a human body depends on a heartbeat. Here's what the data actually shows about where we are in the broader picture. Solar cycle 25 began in December 2019. The sun had been in a deep minimum, the kind of quiet that produces records for spotless days, and causes some researchers to wonder whether the star is entering a new Maunder minimum, a period like the one between 1645 and 1715 when virtually no sunspots appeared, and northern Europe entered what some historians and climatologists call the Little Ice Age. That deep minimum ended. Solar cycle 25 did not just end it, it reversed into something that broke every forecast in the other direction. By October 2025, the sun had fired an X9.0 flare, one of the largest of the cycle. Solar cycle 25 has been stronger than any model predicted it would be, at every stage for 6 consecutive years. And the 10.7 centimeter radio flux, that background measure of solar output standing at 138 solar flux units on May 4th, is meaningfully elevated. For comparison, quiet solar minimum conditions produce values around 70 solar flux units. We are nearly double the quiet baseline. That background energy is what the mystery CME arrived into. That background energy is what it combined with. And the coronal hole now rotating into the central solar disk will add its high-speed wind stream to whatever comes next in the coming days. Let us be precise about what a coronal hole means for what is coming. A coronal hole is a region where the sun's magnetic field opens outward into the solar system instead of looping back onto the surface. Where the normal solar wind might travel at 400 to 500 kilometers per second, a high-speed stream from a coronal hole can reach 700 to 800 kilometers per second or beyond. That stream takes 2 to 3 days to travel from the sun to Earth. The coronal hole observed centered on the solar disk as of May 5, 2026 will deliver its stream roughly by May 7th to 8th. If a CME is embedded in that stream, if another slow transient is traveling in the same direction, the way the March 1989 double CME structure worked, with one plasma structure clearing a path for the next, the resulting storm could be significantly more intense than May 4th. This is not a prediction. This is a description of conditions. The question is not whether conditions are favorable for enhanced geomagnetic activity in the coming days. They are. The question is whether anything is riding those conditions that we have not yet seen. There is a deeper systemic connection that must be made because space weather does not exist in isolation from Earth's other systems. The magnetosphere that is being compressed and stressed and held open during events like this is the same magnetosphere that shields the upper atmosphere from solar energetic particles. When geomagnetic storms occur, ring current enhancements, the intensification of electrical currents circling Earth in the inner magnetosphere, alter the distribution of energy in the ionosphere. That ionosphere is the upper layer of the atmosphere that makes long-distance radio communication possible, that GPS signals pass through on their way to receivers on the ground, and that plays a subtle but measurable role in the way cosmic radiation reaches the lower atmosphere. There is emerging research, contentious, not yet settled science, but serious enough to be published in peer-reviewed journals and noted by sources including the statistical analysis work referenced in the climate and solar research communities, examining correlations between X-class solar flares, enhanced ionization, and seismic activity. The mechanisms being proposed are not proven. The correlations are not causal chains backed by irrefutable evidence. But the idea that Earth is a single system, that what the sun does to the ionosphere can send pressure signals downward, that geomagnetic storms can influence the electrical environment of the lower crust, is a scientific question being taken seriously by serious researchers. The planet breathes as one organism. The magnetosphere, the ionosphere, the atmosphere, the ocean, the crust. These are not separate domains. They are layers of a single connected system, and what happens at the top propagates downward in ways that our measurements are still only beginning to trace. We have instruments. We have DESC over at L1 providing real-time solar wind data. We have SOHO and the stereo fleet imaging CMEs leaving the sun. We have NOAA's new SWFO L1 observatory, which completed its final orbital burn in January 2026 and entered its operational position at L1. We have NASA's IMAP, the Interstellar Mapping and Acceleration Probe, which entered orbit around the Sun-Earth L1 Lagrange point after its September 2025 launch and is now providing real-time data of a type we have never had before, measuring how energetic particles travel from the Sun through the heliosphere to Earth's doorstep. We have more eyes on the Sun than at any moment in human history, and on May 4th, 2026, with all of those instruments running, with all of those data streams flowing into NOAA's Space Weather Prediction Center in Boulder, Colorado, with the most advanced operational space weather forecasting system ever built at full operational capacity. A CME arrived that was stronger than predicted, from a source that was uncertain, carrying a magnetic orientation that held southward for 15 hours and drove a G2 storm. The monitoring is in place. Detection is possible. Prediction is not. And now, at 08 hours UTC on May 6, 2026, as this script is being written and read, the remnants of the May 4th event are fading. The BZ has shifted northward. Conditions are expected to return to quiet to unsettled. KP between 1 and 3. More G1 conditions may occur through the rest of the day and into tomorrow as the coronal hole stream lingers. The large coronal hole recently centered on the disk is preparing to deliver its fast solar wind in the next 2 to 3 days. Active regions continue to evolve on the disk. AR4428 produced a plasma jet captured by the GOE's 19 satellite in the 304 angstrom channel on May 5th, suggesting continued magnetic complexity in that region. The system is not settled. The system is watchful, and so must we be. Because this is the truth that the May 4th storm delivers, quietly but unmistakably, if you are willing to hear it. We live our entire lives dependent on a magnetic field we cannot see, generated by a liquid iron outer core churning thousands of kilometers beneath our feet, interacting at its outer boundary with the solar wind from a star 150 million kilometers away. That magnetic field has protected life on this planet for billions of years. It has deflected the worst that the sun could send. It has kept the atmosphere from being stripped away by solar wind the way Mars's atmosphere was stripped away after that planet lost its magnetic field approximately 4 billion years ago. Mars, now a cold, thin-aired, radiation-blasted world, is what Earth looks like without a working magnetosphere. And every time the BZ turns southward, every time a CME arrives carrying a southward magnetic field and holds Earth's door open for 15 hours, we are reminded that the protection is real, but it is not unconditional. It can be stressed, it can be compressed, it can be overwhelmed, not by a G2 storm, not by a G3, but by a Carrington event arriving in the modern era, carrying a southward BZ of 50 to 100 nanoteslas for 36 hours instead of 15, hitting a civilization that has 8,500 satellites, a power grid built on high-voltage transformers with no spare inventory, a GPS system woven into every hospital and financial exchange and emergency dispatcher on the planet. That is not a thought experiment. That is a documented precedent. It happened in 1859. The geological record says it has happened before 1859. And solar cycle 25, the cycle that was supposed to be quiet, has already produced a G5 storm in May 2024, an X9.0 flare in October 2025, and now a surprise G2 event whose origin scientists cannot precisely identify. The forecasters were watching, the instruments were running, the data was flowing, and the storm arrived anyway, stronger than predicted, from a source that remains uncertain, carrying the one magnetic orientation most capable of opening Earth's shield. And it held that orientation for 15 consecutive hours while the world below went about its day. The question is not whether a larger storm is coming. The question is whether, when it does, the 15 minutes between detection and impact is enough time to protect what we have built.